The modern industrial economy is bottlenecked not by raw mineral extraction, but by chemical refining capacity. Acid-grade fluorspar is the foundational input for anhydrous hydrofluoric acid, or AF. China controls 60% of global fluorspar mining and 72% of global AHF refining capacity. This creates a single point of failure for advanced semiconductor etching and battery manufacturing. While Mexico holds 18% of global mining, it possesses only 8% of refining capacity. The United States has virtually zero domestic mining and relies entirely on imports. This structural asymmetry means Western supply chains remain deeply dependent on East Asian chemical processing. The transition to electric vehicles is accelerating this chemical bottleneck. Lithium-ion battery electrolytes require lithium hexafluorophosphate, a compound synthesized directly from AHF. Global demand for this electrolyte salt is projected to scale from 65,000 metric tons to 175,000 metric tons by 2028. Producing 1 metric ton of electrolyte requires up to 1.8 metric tons of high-purity AHF. This drives annual AHF feedstock requirements for the battery sector alone to over 288,000 metric tons. This demand curve will outstrip non-Chinese refining capacity by 300%. This vulnerability mirrors the Second World War scramble for cryolite, a fluorine mineral essential for aluminum smelting. At the time, the global supply depended on a single natural mine in Greenland. To bypass this maritime choke point, both Allied and Axis powers rapidly scaled synthetic cryolite production using hydrofluoric acid. United States synthetic output rose from 12,000 tons in 1939 to 92,000 tons by 1944. This historical precedent demonstrates that critical material bottlenecks are rarely solved by mining alone. The ultimate arbiter of industrial scaling is advanced chemical synthesis.